Fine. Let's start. Number 10. What the vacuum of space does to a human body. Imagine the airlock fails. 1 second you're inside, and the next there's nothing around you at all. Not thin air. Nothing. And here's the strange part. You don't pop like a balloon, and you don't turn into an ice cube. What actually happens is quieter, and somehow worse. With no pressure pressing in from outside, the water in your body stops behaving like water. Your blood, your spit, the moisture in your eyes and your tissues all start trying to become vapor at your own body temperature. Scientists call it ebulism. After about 10 seconds, the water on your tongue would begin to bubble. You'd start to swell as gases came out of solution under your skin, puffing you up like a slowly inflating suit. But your skin is tough and elastic, so it holds. You stay in one piece. We're not guessing about this. In 1966, a NASA technician named Jim LeBlanc was inside a vacuum chamber at the Johnson Space Center, testing a spacesuit, when a hose disconnected and the pressure around him dropped to near vacuum. He stayed conscious for about 14 seconds, and the last thing he remembered, before he blacked out, was the feeling of the saliva on his tongue starting to boil. That's the number that should keep you up. 14 seconds. That's roughly how long you'd have while conscious, because your body would keep burning the oxygen already in your blood to feed your brain for a little while longer. After that, you're out. LeBlanc was lucky. The crew repressurized the chamber within about half a minute and got to him in time, and he walked away with a mild earache and nothing else. But push past that window, and the story ends the way you'd expect. No oxygen reaching the brain, and the lights go out for good. So forget the movies. Space doesn't make you explode in a red mist, and it doesn't freeze you solid on contact. The real thing is a 15-second countdown, and the sound of your own body quietly starting to boil. You would have just enough time to understand exactly what was happening to you, and not quite enough time to do anything about it. And that's the gentlest thing on this list. Number 9. You would cook before you would freeze. Ask anyone what would happen to you in space, and they'll tell you the same thing. You'd freeze instantly. It's in every film. Someone steps out of the ship and turns into a frost-covered statue in a heartbeat. It makes perfect sense, too. Space is cold. Genuinely, almost unimaginably cold, hovering just a few degrees above absolute zero, the coldest temperature the universe allows. Here's the thing, though. That's not how heat works. To feel cold, you have to lose your body heat to something. On Earth, cold air and cold water are brutal because they're touching you, carrying your warmth away, molecule by molecule. That's conduction and convection, and both of them need stuff. They need a medium. Space doesn't have one. It's a vacuum, which means there's almost nothing out there to touch you and pull your heat away. The only way you can shed warmth is by slowly radiating it off as infrared light, and that is a painfully slow process. So the instant freeze idea gets the physics exactly backwards. You'd hold on to your heat far longer than you'd expect. And if you happen to be in sunlight, the problem flips completely. Out beyond the atmosphere, there's nothing to soften the sun's rays. It just hammers you, full strength, and you have almost no efficient way to get rid of that heat. So you don't freeze. You bake. This isn't a thought experiment for the people who actually go up there. It's an engineering problem they solve every single day. Look closely at what an astronaut wears under the white outer suit, and you'll find a garment threaded with dozens of thin tubes carrying cool water across their entire body. That whole system exists for one reason. Not to keep them warm in the big, scary cold of space. To stop them from overheating inside their own suit while they work. Eventually, yes, if you drifted into the shadow of a planet with no sun on you at all, you would cool down. And given enough time, you'd freeze. But it would take hours, not seconds. A long, slow fade, not a snap. So the coldest place you will ever be is also the place most likely to cook you alive. The vacuum that sits a whisker above absolute zero can't actually reach in and take your warmth. It just leaves you sealed inside your own heat, in the dark, with nowhere for it to go. Number 8. Space is a hypervelocity shooting gallery. We picture orbit as empty, peaceful, a calm black backdrop with the Earth turning gently below. But the space around our planet is one of the most heavily armed environments humans have ever put their bodies into, and almost none of the bullets are big enough to see. Low Earth orbit is littered with debris. Some of it is natural, tiny grains of rock and dust left over from comets and asteroids. Most of it is ours. Flakes of paint, chips of metal, frozen droplets of old rocket fuel, fragments of satellites that shattered decades ago. There are more than 100 million pieces, too small to track from the ground, and every one of them is moving fast. Really fast. In the space station's orbit, an impact happens at something like 9 to 10 kilometers per second. That's over 22,000 miles per hour, many times faster than a rifle bullet. At those speeds, size stops mattering the way you think it should. A fleck of paint stops being harmless and starts being ammunition. In 2016, an astronaut named Tim Peake photographed a window on the International Space Station from the inside. There was a chip gouged out of the glass, a little crater about 7 millimeters across, with cracks spidering out from the center. It looked like someone had shot the window, and in a way, someone had. The thing that did it was most likely a tiny flake of paint, or a metal fragment no bigger than a few thousandths of a millimeter. A speck, a nothing, traveling fast enough to carve a pit into the toughened window of a spacecraft. That window survived because it's quadruple glazed, 4 layers deep, built to take exactly this kind of hit. The parts of the station where the crew actually live are wrapped in shielding, designed to catch and break apart small debris before it can punch through. Every so often, the whole station fires its thrusters and moves out of the way of a piece big enough to track, because a direct hit from something the size of a marble could be catastrophic. And the problem is growing. Every collision up there creates more fragments, and every fragment becomes a new bullet in the same slow, endless crossfire. So the emptiness above your head isn't empty at all. It's a shooting gallery, running day and night, where the ammunition is our own leftovers and the triggers were pulled years ago. The astronauts up there right now are living inside it, separated from the crossfire by a few centimeters of glass. Number 7. Metal welds itself in space. Here's one that sounds like it can't possibly be true. Take 2 clean pieces of the same metal, touch them together in space, and they can simply become one piece. No heat, no welder, no glue. They just fuse, permanently, as if they'd always been a single object. It's called cold welding, and once you understand why it happens, it stops sounding like magic and starts sounding a little unsettling. Down here on Earth, metal is never really bare. The instant a fresh metal surface meets the air, it grows an incredibly thin skin of oxide, a microscopic layer of tarnish. You can't see it, but it's always there, and it acts like a barrier. It's the reason you can rest 2 spanners against each other in a drawer, and they don't merge into a lump. Now take that same metal into the vacuum of space. There's no air, so there's no oxide skin. Nothing forms that barrier. And when 2 clean metal surfaces touch, the atoms on one side genuinely can't tell where they end, and the other piece begins. They're identical atoms in an identical arrangement, so they just carry on the pattern across the join and bond. As far as the metal is concerned, there was never 2 pieces. There was only ever one. This is not a lab curiosity. It has reached out and broken real spacecraft. In 1991, NASA's Galileo probe was on its way to Jupiter, and it needed to unfurl its main antenna, a big umbrella-like structure held closed for launch. The command went out. The antenna started to open, and then it stuck, jammed part way, like an umbrella that won't quite bloom. Several of the metal ribs had rubbed against each other during the journey, worn away their lubricant, and cold welded themselves together. The antenna never fully opened for the entire mission. Engineers now design around this constantly. They deliberately pair different metals that are less likely to bond. They coat surfaces, and they use special space-grade lubricants on anything that has to move. Because they know that up there, bare metal doesn't stay separate on its own. It wants to join. There's something quietly eerie about it. We think of metal as inert, dead, safe. But strip away the thin film of tarnish we never even notice, and it turns out solid metal has been waiting the whole time to reach out and fuse with whatever it touches. In space, it finally gets the chance. Number 6. Astronauts see flashes of light with their eyes closed. On the way to the moon, in the quiet dark of the cabin, the Apollo astronauts kept seeing something they couldn't explain. Little flashes, streaks, points of light blooming in front of them and then vanishing. It happened with their eyes open, and more disturbingly, with their eyes shut. Neil Armstrong and Buzz Aldrin both reported it on the first landing mission. So did the crews that followed. At first, nobody knew what it was, but it was consistent enough, and strange enough, that later missions actually flew experiments to study it. And what they found is one of the eeriest facts about the human body in deep space. The flashes were cosmic rays. Out beyond the protective bubble of Earth's magnetic field, space is full of high-energy particles, atomic nuclei stripped bare and flung across the galaxy at almost the speed of light by exploding stars and other violence we're still trying to understand. And some of those particles were passing straight through the astronauts, through the spacecraft, through their skulls, through their eyeballs. When one of them punched through the eye, it triggered a flash of light inside, even in total darkness. The technical name for that kind of false flash is a phosphene, a sensation of light produced by something other than light. Press on your closed eye, and you'll see a faint glow. That's a phosphene. But this one wasn't caused by pressure. It was caused by a subatomic bullet from a dead star crossing through the wettest, most delicate part of your head. On Apollo 17, the crew ran a careful session, and investigators managed to match individual flashes to specific heavy cosmic ray nuclei, crossing an eye at that exact moment. Once their eyes were fully adapted to the dark, the astronauts saw one of these flashes on average about once every 3 minutes. Sit with that. Every 3 minutes, on the trip to the moon, a piece of the galaxy was passing through your eye and leaving a spark behind. And there's no perfect way to stop it. You can shield a spacecraft against a lot of things, but the most energetic cosmic rays go through metal like it's fog. Every astronaut who ventures beyond Earth's magnetic field becomes, in a small way, a living particle detector. The flashes are the part you can see. The rest of that radiation, crossing quietly through the rest of your body, is the part you can't. Number 5. The sun is slowly getting brighter. The sun looks utterly steady. It came up this morning the way it has every morning of your life. The same size, the same warmth, apparently changeless. But it isn't. Very slowly, over spans of time our minds aren't built to feel, the sun is getting brighter. And that gradual brightening has an expiration date attached to it, one that comes for the Earth long before the sun itself ever dies. Here's why it happens. Deep in the core, the sun fuses hydrogen into helium. As helium builds up, the core slowly contracts and heats, and the whole star burns a little more fiercely. The rate is glacial, roughly 10% brighter every billion years. Nothing you could ever notice. But keep adding it up, and the numbers turn frightening. Because Earth's climate sits on a knife edge with the amount of sunlight it receives. Turn that dial up far enough, and you cross a line scientists call the moist greenhouse. More heat means more water vapor in the air. Water vapor is a greenhouse gas, so it traps more heat, which lifts even more vapor, and the whole thing feeds on itself. The oceans begin to evaporate into the sky, and once that water is high in the atmosphere, sunlight breaks it apart, and the hydrogen leaks away into space. Piece by piece, the planet loses its water to the void, and it never comes back. The models put that turning point somewhere around 1 to 2 billion years from now. Not 5 billion. Not the far future red giant apocalypse everyone pictures. 1 to 2 billion years, while the sun is still an ordinary, familiar yellow star. By some estimates, the Earth could stop being habitable for creatures like us in a little over 1 billion years. That's the part that unsettles me most. We tend to imagine the death of the Earth as fire, a swollen red sun roasting the planet at the end of time. But the real deadline is much closer and much stranger. Long before any of that, the oceans quietly boil away into the sky under a sun that still looks perfectly normal from the ground. No explosion. No warning you could feel. Just a slow rise in the thermostat, running for 1 billion years, that ends with a dry, silent rock where the oceans used to be. The sun that keeps you alive is the same sun that has already started the clock. Number 4. The solar wind is peeling planet's air into space. The sun isn't just light and heat, it's also constantly blowing. A steady gale of charged particles streams off its surface in every direction at hundreds of kilometers per second, and it never stops. We call it the solar wind, and it does something to worlds that you can actually watch happening. It strips them of their air. We know this because we've measured it, right next door, on a planet that used to look a lot like ours. Mars today is a freezing desert with an atmosphere so thin you'd be dead in moments if you stepped out unprotected. But the rocks tell a different story. Billions of years ago, Mars had a thick atmosphere. Rivers, lakes, maybe even a shallow sea. Then, somewhere along the way, it lost almost all of it. The question was where it went. NASA sent a spacecraft called MAVEN to find out, and it caught the crime in progress. The solar wind arriving from the sun is peeling the Martian atmosphere away and dragging it off into space at a rate of roughly 100 grams every second. About 1/4 pound of air, gone, every single second, mostly streaming away behind the planet like smoke off a candle. During solar storms, when the sun flares up, the rate jumps dramatically. And early in the solar system's history, when the young sun was far more violent, it would have been stripping Mars hundreds of times faster than it does today. That's how you kill a planet. Not with a single blow, but by skinning it, 100 grams at a time, for billions of years, until the air is gone and the water it protected boils away or freezes out. And what's left is the rust-colored corpse we see now. So, why are you still breathing? One reason: Earth has a strong magnetic field, generated deep in its molten core, and that field wraps around the whole planet and deflects most of the solar wind before it can reach the air. It's an invisible shield, and it's the main thing standing between our atmosphere and the same slow fate that emptied Mars. Which is a comforting thought, right up until you remember that the shield isn't guaranteed forever, and that the same wind that stripped a whole planet next door is still blowing against ours, right now, patiently, waiting for the shield to weaken. Number 3, the moon is escaping. The moon is leaving. Slowly, quietly, a little more every year, it's drifting away from us, and there's nothing anyone can do to stop it. We know the exact speed, because the Apollo astronauts left mirrors on the lunar surface, and ever since 1969, We've been firing lasers at them and timing the echo. The answer comes back the same every time. The moon is receding at about 3.8 centimeters a year, roughly the rate your fingernails grow. It's happening because of the tides. The moon's gravity pulls the oceans into a bulge, and as the Earth spins, that bulge is dragged slightly ahead of the moon. That misplaced bulge tugs the moon forward, nudging it into a higher, wider orbit, and at the same time it acts like a brake on the Earth's spin. So, as the moon eases away, our days are getting longer. Hundreds of millions of years ago, a day on Earth was only about 22 hours. The moon is quietly stealing our spin and carrying it off into a larger orbit. 3.8 centimeters sounds like nothing, but run the clock forward far enough, and it takes something from us that we will never get back. Total solar eclipses. Right now, we live in an extraordinary and completely temporary coincidence. The sun is about 400 times wider than the moon, and also almost exactly 400 times farther away. That fluke is the only reason the moon can slide in front of the sun and cover it so perfectly, turning day to twilight and revealing the sun's ghostly outer atmosphere. It is one of the most beautiful things a person can witness, and it depends entirely on the moon being just the right distance to appear just the right size. But the moon is escaping. As it drifts outward, it looks a little smaller in our sky each year, and in something like 600 million years, it will have moved far enough that it can no longer completely cover the sun, not even at its closest approach. On that day, the last total solar eclipse in the history of the Earth will happen, and then there will never be another one. Ever. Every total eclipse you've seen, or ever will see, belongs to a narrow window of cosmic time that humans just happen to be alive for. No civilization that comes after that final eclipse will ever look up and see what we see. The moon will still be there. It'll just be too far away to hide the sun. Number 2, the sun will kill the Earth on schedule. Everything eventually ends, but most endings feel like maybes. Distant, uncertain, something that might happen if things go a certain way. The death of the Earth is not one of those. It's written into the life story of the sun, and the equations are almost boringly confident about how it goes. In roughly 5 billion years, the sun will run out of hydrogen to burn in its core. When that happens, it doesn't just fade out quietly. It does the opposite. The core collapses and heats. Fusion ignites in a shell around it, and the outer layers of the sun balloon outward, hundreds of times larger than the star we see today. It becomes a red giant, a bloated, glowing monster swelling across the inner solar system. Mercury goes first, swallowed whole, then Venus, and then it comes for us. For a while, astronomers held out a strange kind of hope. As the dying sun swells, it also sheds a huge amount of its own mass, blowing it off into space. And a lighter sun has a weaker grip, so the planets should drift outward, to safer, wider orbits. For a time, it looked like Earth might just ride that outward drift and slip past the edge of the giant, scorched, but intact. Then the models got more careful. A detailed study found that the escape doesn't quite work. As the Earth moves through the swollen outer layers of the giant sun, it raises tides in the star itself, and those tides drag on the Earth and steal its orbital energy, pulling it back inward faster than the mass loss can push it out. The planet spirals in, and about 500,000 years before the sun even reaches its largest size, the Earth is engulfed, dragged down into the star, and gone. So here is the appointment already on the calendar. Not a comet we might dodge, not a disaster we might prevent. A certainty, baked into the physics of an ordinary star, thousands of times more distant than all of human history is old, but coming all the same. The oceans will have boiled away long before. The planet will already be a dead, dry rock. And then the sun that made all of it possible, that grew every plant and warmed every living thing that ever existed here, will reach out and pull the earth into itself and erase it. The thing that gives us life has a schedule, and our name is on it. Number 1. The night sky is a graveyard of ghosts. Go outside tonight, away from the city lights, and look up. It feels like you're seeing the universe as it is, right now, in this moment. You're not. You're looking at the past, all of it. And some of what you're seeing may not even be there anymore. The reason is simple, and it's one of the deepest truths in all of physics. Light is fast, but it is not instant. It travels at a fixed speed, and space is enormous, so light takes time to cross it. When you look at something far away, you're not seeing it as it is. You're seeing the light that left it long ago, finally arriving now. To look out into space is to look back into time, and there is no way around it. The sun you see isn't the sun of this instant. It's the sun as it was about 8 minutes ago, because that's how long its light took to reach you. That's the small version. Now go further. Look at Betelgeuse, the bright orange shoulder of the constellation Orion. It sits around 640 light-years away. So the Betelgeuse you see tonight is the star as it looked more than 6 centuries ago. Astronomers think it's near the end of its life and could explode as a supernova. Here's the vertigo. It might have already blown up. If it detonated tomorrow, we wouldn't find out for roughly 600 years, because the news, the light of its death, is still crossing that gulf toward us. It could already be a wreck, and we'd have no way to know. Push all the way out, and it only gets stranger. The faint smudge of the Andromeda Galaxy is light that left it 2.5 million years ago, before our species even existed. Everything you see in the night sky is a snapshot from a different era, and none of the snapshots are of now. The sky is not a picture of the universe. It's a collage of 1,000 different pasts, all reaching your eye at the same instant, stitched together into something that looks like a single moment, but isn't. And this is the part that stays with me. You will never, ever see the universe as it truly is. Not because your eyes are weak, but because now, out there, is something light can never deliver. The stars above you are messages from the deep past, and some of the senders are already gone. We live at the bottom of an ocean of old light, looking up at ghosts, and calling it the present. Thank you for watching, and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.